Welcome to the third week video lecture. So today we're going to talk about the Kirchoff's law, Kirchoff's current law, and Kirchoff's voltage law. So before we start that, we're going to revise a bit what we have seen last week. So last week we've looked at several simple DC circuit analysis. So we have looked at basically we have tried to observe what happened to the current and voltages when the loads are put either in series and parallel. So we have understood what happened to the current and voltages as they go through this what we call network of resistances, right? And then following that observation, we have come out with, for example, the calculation of equivalent resistances if they were parallel or if they were in series. And then there are several interesting characteristics that we can use, such as a voltage divider and current divider. So now, after having all the basics element of understanding the parallel and series circuits, what we can do now is we can start to analyze a more complex circuit where we have larger networks. But what we need now is a certain laws that was basically observed in last week, but now we're gonna announce it as a specific law, and we're gonna use it directly as the law mentioned it, right? So the first one is Kirchoff's current law. So what we have seen last week in parallel circuit, we have observed that as we supply current to a circuit network of resistances that put into series, what happens is the current will basically separated into the branches that exist in that circuit. For example, if we a current supply coming from one branch, and then after that the branch is separated onto three branches, the current coming from the supply will be separated into three parts, and will go into the three branches of the output, let's say output, right? So what happened from there is that we can try to calculate the sum of current that gets into what we call a node or a junction. So you may find the term node or junction. Term node or junction refers to basically a point where all the branches are connected to. So we call it node, or sometimes you might find in textbook it's called as junction. So as we measure, basically as we count all the currents that get into that node, counting basically the fact whether it's going in or leaving out from that node, we will find out that the sum of currents at a node in a network equals to 0. So basically it is a consequence of conservation of energy. If we consider there is no leakage of current, if it arrives from a branch, where else could it go? It could only go to all the branches that we have connected to the node, right? So in this example, for example, we have 5 currents and 3 currents that goes into that nodes, I1, I3, and I5, and the other 2 currents, I4 and I2, are leaving the nodes. So the sum of all currents should be equals to 0, because the current getting in or getting out could only come from these 5 branches, right? So the way to write the equation in order to basically take into consideration the Kirchoff's current law is basically by adding up all the current. What you need to do first is basically to identify the direction of current, whether it's getting into the node like I5, I1, and I3, or it's leaving the node like I4 and I2. So the first thing you need to do is to assign a sign, whether it is positive or negative, to the current. So for example, let's say we're going to take here, if the currents get into the node, we're going to consider it as positive, like I1 over here. But if the current is leaving the node, we're going to consider it as negative. So it's just like in mechanical, in dynamic, you're calculating forces. For example, if it's pushing following x-axis, you're going to consider it as positive. If it is pushing against or in opposite of x-axis, you're going to consider it as negative, right? So it's the same thing here in KCL. And then what you need to do is sum up all the current. For example, here is going to be I1, and I1 is positive, minus I2, and then plus I3, because I3 is getting into the node, minus I4, and plus I5 equals to 0. So this particular equation that we've written over here, this is basically what we call the Kirchoff current law. Okay. So now in this particular lecture, we are going to mostly do examples to basically demonstrate this particular laws. So this one is basically the one that looks like the previous slide, but now it asks you to do it on your own. So please try to do it on your own as well. So for network junction shown, so network junction or a node with branches connected shown, calculate the current I3. So the question asks us to find the value of I3 given that the value of all the other resistances. So all the other currents, right? So KCL, remember, Kirchoff currents law is applied on current, and it is applied when you can identify a junction or a node, right? So if you want to apply KCL, the equation of KCL, there is two prerequisites. The first one is that you have to make sure that the equation that you're writing is the equation relating the currents. We don't want to see any voltages or any other parameters. It has to be currents, okay? And then the next thing is that the current has to be identified on a node. So the relation is basically they all need to be connected on a node. You cannot have a multiple nodes, or else the currents are basically not connected to each other. Okay, so let's say I3 equals to 3 amps, I2 equals to 4 amps, and then I4 equals to 2 amps. I'm sorry, I1 equals to 3, I2 equals to 4, and I4 equals to 2 amps. So what you need to do is basically first to identify the direction. Let's say, let's have a look. Let's say we're going to consider the direction that get into the node. The current that get into the node is positive. So I1 is positive. I2 is the current get out of the node minus I2. I3 get into the node positive plus I3. And then I4 is get out of the node, leaving the node minus I4. So the sum of all current equals to 0 as said by KCL. So if you want to find I3, because we know that the other current I1, I2, and I4 are known, are given. If you want to find I3, then you isolate I3, you bring all I1, I2, and I4 to the other side. You'll get I3 equals to minus I1 plus I2 plus I4, which is equal to you'll get minus 3 amps. So the most important thing in KCL, if you want to analyze, find parameters using a KCL, you need to write this KCL equation, and as you can see, the KCL equation says the sum of current inside a node that goes through this node equals to 0, right? So it needs to be an equation of current, and it is on a particular node. So let's say if you have an exercise, you have to identify the node first, and then assign the direction of current, and then write your KCL. It's direct and simple. In this next example, we have four current that get into a section of a circuit. So imagine this is a section of circuit that's put into a box where we have inside it two junction, and then these two junction is connected by basically in upper part we have two resistances R1, R2, and in the middle of the junction we have R3. Imagine if this was a black box where you only able to see the current entering I1, I2, I3, I4, and I5. We can also do an exercise like this. So it asks here, with reference to the network shown, determine the relationship between current I1, I2, I4, and I5. So I1, I2, I4, and I5. Can we write an equation relating with I1, I2, I4, and I5? If we only have the 4 points outside but we don't know what in the middle, of course we cannot we won't be able to write anything, because we don't know what happened in the middle. But we can also imagine that this box could represent one junction or one node where we have connected between them. Basically, imagine if the box are represented by one junction or one node, you have I1, I2, I4, and I5. So you have I1 over here, I4 over here, I2 over here, and I5 over here. So from the point of view of someone who does not have access to the box, it will see something just like this. From this point of view, the question asks, what is the relation between I1, I2, I4, and I5? So for us, what we need to do is basically to open up this node and look what happens inside it in order to be able to write down the relationship between them, right? So what we can do is basically when you open it up, we see that there is a node A and node B, or junction A, junction B. We can write equation in KCL in A in order to relate I1, I4, and I3. And then when you write KCL in B, you will be able to relate between I3, I2, and I5. Of course, we will have two equations, and then we will eliminate I3 because I3 is the one that relates between the upper branch and the lower branch, and we will eliminate I3. You will basically join or connect the both branches together to become something in a simpler form like this. So let's have a look at the answer. So in junction A, we can write basically the relationship between I1, I4, and I3. So it's I1 plus I4 minus I3 equals 0. And for junction B, we can write I3 plus I5 minus I2. So I3 getting into junction plus I5 get into junction minus I2 equals to 0. Therefore, in both parts, we have I3. We can eliminate I3 by writing everything in function of I3. So I3 equals to I1 and I4 in junction A. But I3 is also equals to I2 minus I5 in junction B. So both of them are I3. So we put them in equals. So we will get, therefore, as mentioned in here, I1 plus I4 equals to I2 minus I5. So you don't have I3 anymore. This is the relationship that is now representing the one that we have over here, relation between I1, I2, I4, and I5 without I3. So what we can see here, we can conclude that multiple node like A and B over here could be joined together and considered as what we might call in certain textbook as supernode. So if the thing that is happening inside here doesn't interest us, for example in I3 is it doesn't interest you to know what happened in I3, we can group them together to be able to write a KCL that relates the current that interests us. So for this example, the current that interests them is basically I1, I2, I4, and I5. Now let's try the next exercise. So this one is the network is a bit larger. You have multiple. So this is the DC power supply. What we have is a current. So as we mentioned, KCL is related to calculation of current. So we don't need to identify what the voltage is. If it were given a voltage, then you have to deduce what the current is, right? So let's say this one is pretty simple. The current is given. So we have basically multiple nodes. So we can see that the nodes are identified by the letters. This is one node called node A. There is another node at the bottom called as node B. And then there's a node at the middle called as node C, node or junction, right? So node or junction is basically connection of multiple branches. And then of course, here there is another node, but it is an unidentified node. There's no mention of what's going to be called. You might call it as, for example, if you want to call it, you might call it as node D. But this exercise, what it asks for is basically it asks for you to write down the current relationships. So basically write down the KCL equations for junctions A, B, and C. So you can see the node of junctions A, B, and C of the network shown, and hence determine the currents I2, I4, and I5. So it is a very guided exercise. Basically what happened is at the end, the objective is to find I2, I4, and I5. What is I2, I4, and I5? So I2 is the current that is circulating in this branch through this resistor. It's circulating from, it gets out of node A and it gets into node B, right? So there is a relation between node A and node B. I4 is the current over here in this particular branch that get out of node C and get into node B. And what about I5? I5 is, where can I find I5? So I5 is over here. It is basically the resistance that leaving node C and get into this node that we don't have a name. Let's call it as node D. Okay. So what you need to do is, in order to find this, of course, in order to find I2, I4, and I5, we were given with three currents that is already identified. I1 equals to 3 amps, I3 equals to 1 amps, and I6 equals to 1 amps. So if we already have these three current, what we can do is basically write, what we need to do is we have to write a KCL where we could have the unknown currents and the known currents and try to rearrange, isolate the unknown currents in order to get its value, right? But now we are given with a certain clues. It asks us to write KCL on junction on node A, node B, and node C. So let's have a look at node A first. What we can write in node A. So node A is over here. There is 3 currents that is involved in node A. I1 that gets into it, I3 and I2 that's leaving. So we could write, for example, if we assign the current that get into a node as positive and the currents leaving the node as negative, therefore we could write as I1 equals to I3 plus I2. Let's have a look directly at the answer. We can have a look. So for junction A, as I mentioned, I1 getting into the node equals to I3 plus I2. So I1 equals to I3 plus I2. Or if you bring to this side, I1 minus I2 minus I3 equals to 0, right? So I1 is positive, get into, I3 and I2 is negative, gets out. So I1 minus I2 minus I3 equals to 0. Or as I mentioned earlier, you could also write as I1 equals to I2 plus I3. Current entering node equals to the current leaving the node. It's the same thing, right? What we need to find here, as mentioned in the equation, we want to find I2. So here I1 and I3 are known. If you want to find I2, therefore I2 equals to I1 minus I3. You bring I1 and I3 over here, right? So you get minus I2 equals to I3 minus I1, or I2 equals to I1 minus I3. Therefore, we get 2 amps. The same goes for junction B. So if you look at junction B, let's try to do it first before we look at the question, look at the answer. In junction B, we have I2 and I4 get into it. So I2 plus I4 minus I6 equals to 0. So I2 plus I4 minus I6 equals to 0. And then we know I6 and I2, because I2 we have calculated it previously. So we got I4 equals to I6 minus I2. I6 is 1 amp, as you can see over here. Minus I2, it has been calculated previously, equals 2 amp. So we got minus 1 amp. So what does it mean when we have minus 1 amp? So this is something that you need to particularly understand. If we say that I4 equals to minus 1 amp, if we look at I4, in the exercise, they have assigned the direction of I4 into that the current basically goes into node B. But if we found out that the current is minus 1 amp, it means basically the current is not entering node B, but it is basically leaving node B. So it's negative because in reality the direction is in opposite to what have been shown in the figure. Okay. So and for junction C or node C, this is very simple. We have calculated I4 previously. We know I3, therefore I5 is in relation to I3 and I4. So the KCL first that we need to write is getting into current. So I3 minus I4 minus I5 equals to 0. So I3 equals to I5 that we want to find. I5 equals to I3 minus I4. I3 we have calculated it previously. It is given here. I3 equals to 1 amp. And then I4, as we mentioned, I4 equals to minus 1. So minus 1 becomes plus 1. The answer becomes 2 amps. So it's very simple. It's very straightforward. It's just isolating. So you do the algebraic operation as usual, finding the unknown. But the most important thing is to be able to write the KCL first. Identify the node, as mentioned here, A, B, C. Identify the node, identify the current that getting in, getting out, and then write your KCL. Let's go to the next exercise. So now this exercise, in this exercise we have one supply, we have current I1, which is unknown. So I supply is unknown. It gets into one resistor and then separated into 2 branches. So there is a node or junction here, separated into 2 branches, R2 and R3. And in R2 we call the current as I2, in R3 we call the current as I3. And the only current in these three branches, so we have a junction where there is 3 branches, I1, I2 and I3. The only current that we know is the current in 1 amps. So we can write, of course, the KCL in the middle over here as I1 is positive, minus I2 minus I3 equals to 0. But we cannot find I1 and I2 because we only have I3. So in the equation we have one equation. We have one equation because we have one junction. And then the problem is that we have 2 unknown. one equation with two unknown. We know that in solving a system of equation, if you have a certain number of unknown, you need this also the same number of equation. But now we have two unknown, I1 and I2, and only one equation related to KCL in this junction or in this node. So what do you need to do? So what we need to do is that we need to figure out what is one of the current between I1 and I2. So here what you can do is you can recall the course, the lecture of last week. In lecture of last week, we have something in the configuration of parallel like this. With result of the observation, we have basically found out that we can create what we call as current divider using parallel circuit, right? And then if we know the current I3, and then we know that all the resistances R1, R2, and R3, we can calculate the ratio of current divider, therefore find the current of input current. So let's have a look at the answer. So we'll use first what we call as the current divider in order to basically relate between I supply and I3, right? Because I3, which is 1M, is a portion of I1. So what is the portion? The portion is basically equals to I1 multiplied by the portion, the ratio, which is R2 divided by the sum of R1 plus R2, right? So R2 divided by R1, R3 plus R2. So in this equation, we know what's the value of I3 is, therefore we can find I1. So using this calculation, you'll find out that I1 equals to, so you rearrange the thing, right? So you want to find I1, so I1 therefore equals to R2 plus R3 divided by R2 multiplied by I3. So this is what we're doing over here. If you plug in the numerical value, you get I1 equals to 1.5 amp. So now you have two currents, I1 and I3. The only current that you don't know now is I2. You can use, therefore, now you can use the KCL at this junction. So KCL at the junction, as I mentioned just now, I2 plus I3 minus I1. We can write like that. So it's the same thing as I1 minus I2 minus I3 equals to 0. So if we isolate I2, we'll get I2 equals to 0.5 amp. So basically 1.5 amp coming from I1 from supply, and then it is separated. In I3 we get 1 amp, in I2 we got 0.5 amp, right? So because if you look at the resistance is 2 times bigger as the resistance in R3, therefore the current will be 2 times smaller compared to the current I3. So 1 amps over here, 0.5 amp over here in across the branch R2. So easy. So this is basically the combination of what you have learned previously, current divider with KCL at the same time. Next we are going to look at Kirchoff's voltage law. Just now it was Kirchoff's current law, coming from the fact that a parallel in a parallel circuit you have your current divided into the branches. And now we're going to look at is the other one, which is related to the series circuit, which is Kirchoff voltage law. So in Kirchoff voltage law, now we see that our circuit is in series configuration. We have our EMF supply coming from a DC supply over here, and then we have 3 resistances, for example, and the resistances are basically across all the resistances we can find out the potential difference. For example, here let's imagine this first resistance is called as R1, R2, and R3. So the voltage or the potential differences across the resistances, we could call it as V1, V2, and V3, right? So what we have seen is basically the sum, the voltage that is supplied equals the sum of the voltage that is consumed by the resistor. So we can write from a series circuit, we have observed that. So we can write basically an equation. We can come out with equation from that observation. We can say that the sum of voltage in a loop equals to 0. Okay, so now in KVL there is 2 prerequisites for it. The first one is to be able to identify what we call a loop. So a loop is basically when we have a connection, a network of a load and supply, or even if you don't have supply, a connection of a few components in what we call in series configuration. This is what we call a loop, right? And then what we need what we are accounting for in KVL is basically the voltages. It's not current. So we will come up with equation. So as we mentioned, as we look over here, the equation underneath here. So the equation is basically the equation related to voltages. Okay. So what we can write is basically, in order to write this particular equation, there are several methods. There are several steps, just like in KCL. The first one is you need to assign the direction of voltage. So as we have looked in previous weeks, the assignment of, or when we assign the direction of voltage, we draw basically an arrow, and the way that we draw an arrow is basically the origin of the arrow is the point where you have a lower potential energy, and the tip of arrow is basically the point where you have the higher energy, right? So therefore, in relation to current, if you have, for example, this kind of DC supply where the EMF is in this direction, so this is the negative terminal, this is the positive terminal, you have current getting out of it. So the EMF is in the same direction of the current, but for the load that consume the energy, the direction of the voltages or the direction of potential difference is in opposition to the direction of current. Why? Because we have when the current get into it, we have higher energy, but as the resistance consume it at the output, or when the current's leaving the resistance, level of energy, we could consider it as smaller. Therefore, when we draw the direction, the arrow representing the potential difference or the voltage across the resistance will be in this direction, right? So the first one is to basically assign the direction. So you need to draw arrows across the components, the loads, and the power supply inside your loop. So the first one is to identify a loop and then identify the direction of the voltages or potential difference. Okay, and then what you do is basically you you go around or across the loop. You select a certain direction. Let's say you're gonna select the direction of the current, and then you go through the path of the current and you add up all the voltages. So let's try this. So we have, for example, we start at the supply, we have E, and then as we go through the loop, we encounter V1, and V1, the direction is in opposite of the current loop. So E minus V1 minus V2 minus V3, and then we have no more, equals to 0. So E minus V1 minus V2 minus V3 equals to 0. Or we can also write, therefore, if we isolate E, E equals to V1 plus V2 plus V3. It's the same thing, right? E equals to V1 plus V2 plus V3 is the same thing as E minus V1 minus V2 minus V3 equals to 0. So this is what we call the equation that's coming from your Kirchoff voltage law, or KVL. So we're going to use this basically in order to identify or to find a certain voltages that is unknown in our circuit analysis. So let's try several exercises. The first exercise, it asks us to determine the voltages of V1 and V3. So let's have a look at the circuit. In this circuit, we have a circuit of multiple loops. So just now, as we mentioned, the prerequisite to write the KVL, the first one, if you have to identify the loop, the equation needs to be the equations relating the voltages to, and then therefore you have to assign the direction of voltage, and then go across through the loops and sum up all the voltage, right? So the first one, identify the loop. So how many loops do we have in this circuit? This is very important. So as we can see, we have basically 3 loops. We can identify 3 loops. The first one is this one, what we call as loop A. So the current can circulate in this loop, right? There is a circulation in this loop. We have a second loop, loop B, where we have the circulation in this loop. So in circulation in this loop, we only encounter 3 resistances, no supply, but it is nonetheless a loop where current can circulate. And then we have what we call the larger loop, outer loop over here, where current also circulates. You can identify current circulating across this pathway. So we have 3 loops, loop A, loop B, and the outer loop, we call it as loop C. So we can write, therefore, if we have 3 loops, you can write 3 equations of KVL. What you need to do is just identify the voltages that is involved in each loop, right? So in this particular exercise, it asks us to find V1 and V3. So let's have a look where is V1 and V3. V1, we have V1 over here, and then we have V3 over here. So V1 is basically involved in loop A and loop C. V3 is involved in loop B and loop C. So loop C is the one that's joining them. Therefore, if you want to find them together, you need to write equation in loop C. But if you want to find them alone, you can write the equation related to loop A. So let's have a look at the answer. How do we do it? We can try. In order to do this, we know that we need to isolate the unknown. So the unknown is V1. If we write it in loop C, what happened? If you write it in loop C, you will find there is the supply EMF E equals to 12 volts. And then in loop C, you will encounter minus V1, minus V2, and then minus V4. V4 is known as 2 volt, and then you have nothing else. So in this loop C, you have two unknown, V1 and V2. So you cannot find V1 and V2 by using just only this loop, because you have one equation with two unknown. So let's have a look at loop A and loop B separately. In loop A, you will encounter the EMF 12 volt minus V1, and then you encounter V2, which is known, and then no other. So you have one loop, you have only one unknown. Therefore, in order to find V1, you have to write the equation related to loop A. Let's have a look at loop B. Loop B, the same. You will encounter the 8 volts minus V3, V3, I'm sorry, which is unknown, and then V4, which is known. So in this loop, you can write one equation with one unknown. So this loop can also solve the unknown of V3. So what we need to do is basically write two KVLs of two loops coming from two loops, loop A and loop B. So if you look at loop A, in loop A we can write E equals to V1 plus V2, because if we go through the loop, we will see that E minus V1 minus V2, because the direction is opposite, right? As we assign the direction of voltage, E minus V1 minus V2 equals to 0. Therefore, E equals to V1 plus V2. And then we know what value of E is, what value of V2 is. Therefore, we can find V1, which is 4 volts. The same goes for B. So in B, what happened is you sum up all the voltages that go across the loop. You will find that you have 8 volts minus V3 minus V2 equals to 0, right? So V2 minus V3 minus V4. So V2 minus V3 minus V4 is the same thing as this one, because if I bring all the equation to the other side, you'll get V2. You change the sign, right? So this one become positive, V2. This one become negative, minus V3 minus V4 equals to 0. But here it is written on this side of the equation. It's the same thing, don't worry. It's just that usually when we write equation methodically, we like to write the EMF on one side and the potential difference on the other side, but it is still the same thing. You can write in whichever direction you wish. So in this equation, we know what is the value for V2 and V4. Therefore, in order to find V3, you just isolate V3 and we get 6 volts, right? So remember, in KVL you have to identify the loops and you have to assign the direction of voltage, and the equation of KVL is written in voltage. So we don't want to see when you write KVL using a loop there is a current in here, because there should not be a current. KVL is a law related to voltage in a loop. For loop C, so we have loop C also. Let's just take a look if we can verify using loop C, because we have found what V1 and V2 is. If we calculate through loop C, is it in accordance of what we have found? So in loop C, basically we have, if we go through the circuit, the EMF 12 volts minus V1 minus V3 minus V4 equals to 0. Therefore, E equals to V1 plus V3 plus V4. Right? E equals to V1 plus V3 plus V4. So we have found V1 and V3, 4 plus 6, plus V4 given 2, it equals to 12. So we have confirmed that we have found 12 equal to 12. So the result of V1 and V3, we can confirm that the result obtained for V1 and V3 is correct. So we have basically verified the results. Okay. This second exercise might look a bit complex. So This is basically a form that what we call as a Wheatstone bridge. This is basically a form that you may usually find in a circuit for signal conditioning in a sensor. So imagine you have a sensor just like basically it's usually used for deformation in gauge sensor to measure basically the displacement on certain points on a material mechanically. So what we do is basically we try to measure that there will be a variation of this resistance, and we could measure in output the voltage between this point A and B, right? So this is the purpose of this kind of configuration of resistances network. But regardless what is the purpose or what is the function of it, let's have a look at what the question asks us to do. So here it asks us to calculate VAB for the network shown. So it wants us to find the voltage, the difference of potential between point A and point B. So in between point A and point B, we can see that there is basically two resistance over here. If you want to go through from point A to point B, we can go through this this path A to C and C to B. There is these two resistance R1 and R4. So if you want to find VAB, what we can do is basically we can calculate, write a KVL inside this particular loop from A, C, B, A. So this is also one loop. So the loop doesn't need to be connected by only the wires. We can jump across the wires, but the most important thing is that the voltage that I measured now is basically between VA and B. So imagine if you have a voltmeter, you put one probe on point B, one probe on point A. So you're basically connecting this with a wire where you have a voltmeter in between. You're calculating VAB. So what it needs now is what is the voltage between VAB. So in order to find VAB, we can write a KVL. Let me help you to do this. So you can see that in here, we can write a KVL. This is can be considered as a loop if we put a voltmeter over here. So the loop over here, if we write the voltages, if we assign a voltage across R1 and R4, let's say I'm going to call this voltage between point A and point C as VAC, so voltage difference between point A and point C, and this voltage I assign direction of voltage VBC. So if we do the KVL inside here, so this is VAB, we can write that VAB equals to, or VAB if we write in a sum form, so VAB minus VAC plus VBC equals to 0. So therefore, if you want to find VAB, VAB will be equals to VAC minus VBC, right? So if you want to find VAB, what we need to do is to find VAC and find VBC. So VAC is this voltage over here, VBC is this voltage over here. So how do we find this VAC and VBC? So you will be using the properties that we have seen in previous week. If you look here, you have an input voltage of 20 volt, and the voltage is basically goes in parallel with this part of branch and this part of branch. So in each branch, if I draw the two branch, you will have, if I redraw it, you will have 20 volt over here, and then there is basically two branches in parallel where you have in here it's R1 and R3. Over here you have R2. I'm sorry, you have R2 and R4, and VAB is basically in between this point, VAB, right? So the VAC and VBC that you're looking for is basically it's this point, VAC, this is VAC, and this is VBC. So what you can see here is basically VAC is a portion of the whole voltage, and VBC is also a portion of the whole voltage, which is in parallel with 20 volt. So you can write what we call as a voltage divider, right? So we're going to apply what we have learned in last week, which is voltage divider. So let's look at the answer. So for branch A, so what we call is branch A is where we have this VAC over here. I'm going to take my pointer, branch A. So we can find that VAC is a portion of this branch A. So VAC would be equals to R3 divided by sum of R1 plus R3 multiplied by 20 volts. So you get 7.5 volts. And VBC, VBC is a portion of this branch. So it is R4 divided by R2 plus R4 multiplied by the input voltage, which is 20 volt. So you get 4 volts. So you have in VAC 7.5 volts. In VBC, you have 4 volts. So going back to the KVL you have written just now, VAB equals to VAC minus VC. So you just plug in VAC that you have found. VAC is 7 minus VBC is 4. Therefore, you will find that VAB, if we measure, put a voltage between point A and point B, we will get 3.5 volts. So the configuration of the network might seem a bit complex, but you have to just, in order to write KVL, just identify the loops where you could write your KVL. And then of course, if you cannot manage to find the voltages, you try to use everything that we have learned. So one of them is basically voltage divider. Now the next exercise, we have a circuit with basically 3 loops. So one loop here, one loop over here, and the outer loop. Now we have multiple power supply, E1 and E2. We have 3 resistances where the direction of the voltages are indicated, V1, V2, and V3. So what we could find, what we could try to find is basically the unknown, of course. The unknown parameter here is V1 and E2. So we will have, for example, in this case, find E1 and V1 and E2. So again, as we want to find V1 and E2, they are voltages. So you can apply KVL. What you need to do next is to identify the loop in which you can find them. So V1, for example, is situated in this loop where you have 3 voltages. The EMF, you know the value. V2, you know the value. So using this loop, you will be able to find V1. And for E2, E2 is situated in this loop. So you will be able to find E2 by writing KVL in this loop, because you have 2 unknown, V2 and V3. E2 is the only unknown. And after you have done that, what you could do is you could write your KVL on the outer loops and verify whether the value that you found for E2 and V1 confirm with the KVL that could be written for the outer loops. So let's have a look at the answer. So the first one is for the left hand loop, as we mentioned, V1, V2, and E1. So the equation is EMF E1 equals to V1 plus V2, right? So, or E1 minus V1 minus V2 equals to 0. That gives you V1 equals to 4 volts. On the right loops, right hand loops, you will have basically, if you write the KVL, you have V2 plus V3 minus E2. So V2 plus V3 minus E2, or minus E2 equals to minus V3 minus V2. So this is the equation over here. You will end up getting E2 equals to 14 volts. And then just to check your result, you could go through the outer loop. So you will have E2, for example, minus V3 minus E1 equals to 0. So there are 4 voltages, E2, V3, V1, and E1. So this is the KVL. Alright, so or I was going through the other direction. You could also the direction on which you wanna go through is basically it's no problem at all. You can choose any direction because whether you go through the clockwise or counterclockwise, what happened later, there is an equation, you moving just the equation from one side of the equation to the other. Negative become positive, positive become negative. So if you do like in this particular correction, it is E1 minus V1 plus V3 minus E2 equals to 0, or E1 minus E2 equals to V1 minus V3. So you will get basically 10 minus 14 equals to 4 minus 8. So they are all equal. 10 minus 14 is basically minus 4. Here you also get minus 4. So it confirms the value of V1 and E2 you have found. And then finally, of course, when you do KVL, you can also calculate the power, just like in last week. In your circuit, when you have calculated all the voltages or all the current, you can also calculate the power. For example, the power supplied by a power supply is, of course, the voltages multiplied by the current that is supplied, and then the energy or the work produced by that power supply, of course, is the power multiplied by how much time you are delivering that power. or if we develop P into V multiply I, it will become VIT. So we have done this last week, so it's the same thing. There is several example over here that you may look. So there are two exercises. So it's basically just a calculation of power. Power supplied is P equals to V multiplied by I. But of course, last week we have looked at the power consumed by the resistor. It was Ri square. But at the end, in a complete circuit, the amount of power supplied should be equal to the power consumed. So Vi of all the power that is supplied in circuit should be equal to the sum of Ri square of all the power consumed. That's all the equation that you need to know in order to calculate power and work that is consumed in a circuit, right? So there is another example here, quite easy example. That is basically this time it is related to what, as I mentioned just now, is on the consumption side, resistor. So resistor basically consume your energy and convert it into heat. The equation is Ri square for power. So power represents how much energy you spend per second. So when we say that something is powerful, it means it can debit a lot of energy in a short moment. But if you want to calculate the energy is basically the amount of power multiplied by the duration that you supply that power. So it is basically power multiplied by time. So if power is Ri square, then it is Ri square multiplied by T. So this is on the side of the consumption. So that's all for this week. So there is another this is an example of calculation that is pretty easy that we have done basically last week. So now we have looked at we have arrived at week 6. Week 4. We are close to 1/3 of the semester. We have learned the most important basic fundamental of circuit analysis, which is KCL and KVL. So we will be having, of course, our test 1 in week 5. We'll be revising all the concepts that we have done until now from week 1 to week 4. And I hope you will be able to revise all the material that we have seen, and we'll make some revision in week 5 before we go into midterm test. Not midterm, I mean test 1. Okay, thank you very much, and I'll see you next week. And of course, tomorrow there's the tutorial session with the tutor. Until then, goodbye. Thank you very much.